Alright, let's continue with probability. Today is chapter 15, which is fine. 15 is about continuous random variable. So a continuous random variable is one that can take any value in an interval of the real number line. Okay, think about a measurement. Okay, so a continuous random variable is one that can be measured, where a discrete random variable is one that can be counted. So here's the main difference. So anything to do with measurements like length, mass, duration is considered as a continuous. What is just done is an estimation. So a person's weight in kilogram can be measured to the ith decimal place. So 83 kilos, for example, implies that that's where the mass the weight is in between those two values to one decimal place. Okay, but if you have 83.0, it can also mean this. Okay, and as you increase the number of decimal places, you can see that as you increase the number of decimal places, that's you narrow down the interval. Okay, so it's nothing new that you've learned, it's just an example and maybe a clarification. Alright, let's apply that to probability. So we learn about functions. We're going to narrow it down to what we call a probability density function. Okay, so for a continuous random variable, we define a probability along that interval to be the integral of the probability density function. We're going to add a few more conditions. That function is always positive or equals 0 for whichever domain it is defined. Also, the integral across the whole domain from negative infinity to positive infinity has to be 100% or 1. If the function is undefined, you can also use that notation, like when you reach the you can't calculate the integral because the boundaries are infinite. You will also use the limit notation to try to estimate the that overall integral. That's another way to solve it. What it means is f is scaled so that the total area is 1. It's something to keep in mind, as later on we'll talk about normalization. Now, on the contrary of a discrete variable, when you have a probability that takes a specific value, it's always equals 0 for a continuous variable. Think about it as when you do your integral, if you you calculate the area from A to A, your rectangle area is 0. So that's the same idea. Alright, what it looks like. So the function is above 0. When you determine the area, the integral or the probability from A to B, it's the area under the curve or the integral, because the function is positive. Okay. All right. First exercise example. So you have this function. Between 0 and 2, it's linear. You don't know the C value. That's why you need to figure it out. And below 0 and above 2, it's 0. Okay. So to find the C value, you anti-differentiate from across the whole domain. But because the function is 0 outside of that interval, we can just anti-differentiate from 0 to 2. That needs to be equal to 1. We apply our rule of anti-differentiation. We could take the C out, but because it's linear, we anti-differentiate that is a quadratic. from 0 to 2, we substitute the value and we get that nice equation that we can solve for C. So C is equal to 1 over 2. So that's part A. Alright, with part B, we need to find the probability, the following probability. So we write our integral. Remember, our function becomes 0 after 2. So we can split it into 2. This is going to be 0. This part we anti-differentiate. We substitute the values and we get our answer in exact form. Notice when you anti-differentiate, because it is a probability answer, it has to be between 0 and 1. If your integration is different, then you made a mistake along the way. So here is our probability with 2, which is this one. Okay. Now we need to find that probability from 1i. Because it's a complementary probability, we can use 1i to solve it instead of determining the integral, which is going to result to be 9 over 16. Alright, now to be exactly equal, it is 0. Always the case for a continuous random variable. Alright, exercise 2. To graph this, so you have 0, it's going to be a hybrid function. So anything that is above 1 and below 0 is going to be along the x-axis. Between 0 and 1, it's a parabola. It's actually in turning point form. So if you were to expand it, you can find the turning point coordinates. Okay, so as I mentioned, here you have 0 above 1 and below you have 0 as well. So strictly greater or less, so you exclude the boundary. Here it won't matter because it will merge with the quadratic, but here it's going to be separated. So our turning point is 0 and 3. So 0 and 3, that's the coordinates, and that's an upside down parabola, and that intersects at x equals 1. Okay, to show that it is a probability density function, reading from the hybrid function, we already know the function is positive along the interval, included 0, so that's fine. Then we need to anti-differentiate across the whole domain, which is only from 0 to 1. You solve it, and that gives you an answer of 1. You need to show you're working out all the steps to get full marks. It's just a reminder. Okay, so that's our conclusion statement, and we can assert that f is a probability density function. Okay, find the probability that is x is less than 0.5. We set up our integral from negative infinity to 0.5, so it's going to be restricted from 0. Anti-differentiate, we set our boundaries on the right hand side, we substitute, we simplify, and we get this answer. Alright, another example. You have an exponential for the positive x values. Here at 0 will give us 2, which is excluded. Notice how it is excluded. And then from 0 to the negative values, it's 0. Now when you anti-differentiate, it doesn't really matter to include or exclude, because you can anti-differentiate exponential over r anyway. Again, the function is positive. Exponential is a positive function. 0 is also a 0 function, which is fine. We want to find the whole integral to be equal to 1. We're going to restrict it to 0 to infinity, which is 0 to infinity. Like here, what you should apply is a limit notation actually. So here that's going to be 0, that's going to be 1, and that gives us the whole integral is equal to 1. So f is a probability density function. Next, find the probability that x is greater than 1. So we set our integral from 1 to infinity. Again, you're going to have to use limit notation. So here they use infinity. It's kind of a shortcut. We shouldn't use limit. It's just safer. And here we go. This one again converged towards 0. So what's left is 1 over e2 squared, and that's the exact form. Another way, alternate method. You can use the complementary. So from 0 to 1, which I prefer because now your boundaries are defined, definite. They're not like infinite, so you won't have to use a limit. And we evaluate and we get the same answer. Alright, and that's it for the start of continuous random variables. And I'll see you next session.